Hello, this video is entitled Greens Theorem, which Greens Theorem is going to be a method of using a double integral to evaluate a line integral under the certain conditions. Now, we don't have issues like it has to be a conservative vector field. That does not apply here. And this is Mr. Green over here. Looks like a photo from the Old West, if you ask me, but is he a good guy or is he a bad guy? Well, since he's a mathematician, that automatically makes him a good guy. So, with that being said, if your path is, your curved path takes a pattern to where it's simply connected, just means connected, no gaps or anything, where its orientation to where the shaded area would be on the left of the path, because that's what we're going to convert this to a double integral. So you see, and got to, okay, I don't know what happened. That page just closed for a second or something. But anyway, the curved path will have where the shaded region stays on its left. So you see how this moves along, like along here, and the area is to its left. So you're going that way to the left, facing downward, it's on the left. Same thing here. This one goes this way, the area is to the left, goes that path to the left, this way as it's heading down to the left again, and the circle as it's going counterclockwise will have its area on the left. So that's important to be able to use Greens Theorem. So this Greens Theorem, in other words, is helping us to simplify multi-paths. In other words, we'll have to do each of these paths because we're not necessarily working with conservative vector fields, which we've already learned. You know, you can just take any path from point A to point B and it's fine, but not here. So if not, these would be, well, this would not be multiple line integrals. It would only be one because it's one pattern there, but this would be 3 right here. This would be 2. This would be 3. Now they wrote the lines theorem, the line integral in differential form here. So I'm assuming that's the way we should see most of these, where it's m dx plus n dy. Now here's what Greens Theorem says. I didn't choose these fonts very well. These integrals are so small. So we go back to the double integrals. We take a double integral across the area region of our integration of this formula right here. Means you take the n partial with respect to x minus the m partial with respect to y. That's going to give you a function of x and y's. Nothing is being converted to t's using Greens Theorem. This is literally going back to evaluating a double integral in terms of x and y. So no parameterization involved here. It's strictly a double integral of that formula right there. Of course, dA, that means whether you choose dy dx, dx dy, or polar, r dr d theta is a fair game here. If polar works, we would convert, after we've made x's and y's, we would convert that to polar. So let's give this a whirl. I think it's not too bad, obviously, as long as the integration's not too rude. I don't like for them to get too out of hand myself. So it's a fun little theorem. So we're going to evaluate this vector field written in differential form on this path right here. It's a region inside the semicircle, 20 square root of 25 minus x squared, and outside the semicircle, square root of 9 minus x squared. So what I did is I sort of shaded these two half circles and I drew a path. You know, we're not going to actually use the path. Well, I did it in Maple, which I'll show you here in a minute, but Greens Theorem's so much better. But anyway, so here's the two shaded regions, and if I had a path, I could go, in other words, going in a direction where the area is to my left. So if I take that line segment horizontally, the area is on my left. If I come around the curve this way, as it's going that way, think of it as you're looking at it. I know it looks like it's going down, obviously, but pretend like you're riding on that curve and the area would be to the left. You come here, it goes this way with the area on the left, and then as you traverse the path this way, again, the area would be on its left. So as a regular line integral, you would have to develop 4 paths, and we would have to add those 4 paths together. But since that satisfies the condition of the Greens theorem where it's closed, connected, areas on the left as you go, you just set this up as a double integral and evaluate of the function. And I wrote this notation here, nx minus my, instead of using the fancy partial notation. This one actually happens to work out really easy because there's no x's and stuff here, but we have nx right here would be 2, and then my, the y partial, this one would be 1. So really, in this case, this formula is just 2 minus 1. Now, to integrate 1 basically across this area region, you definitely want to convert this to polar. It's so much easier. You don't want to use these square roots and stuff. Definitely polar because it's circular. So we've had this kind of problem before where we had an inner radius and an outer radius. So the inner radius is 3, the outer radius is 5. We're going from 3 to 5, and then 2 minus 1 from the Greens formula here. And then, of course, that's halfway around, so it's 0 to pi. So we perform this integral, and, of course, r d theta, which makes it 1/2 r squared, 5 to 3. That's 25 minus 9 is 16. Half of 16 is 8. And then 8 d theta from 0 to pi is just going to toss a pi in there, and it's going to make it 8 pi. So that would be the evaluation of that line integral. Now, take a look at this. Now, I didn't show all the steps to this. I just kind of sort of did this in my head and I didn't do the integration in my head and then put it in maple. This maple integral represents the 4 paths that I was talking about earlier. The line, then a curve this way, then another line, then another curve. Actually, I have them a little bit out of order. I apologize for that. It doesn't matter. Mathematically, it's right, but to follow the order, this part right here should have been third, and then this one should have been last. But anyway, it's correct mathematically. But look what all that yielded, 8 pi. But you see, that might not have been so much fun coming up with all that, would it? Devising all the paths and everything. And now, here, what I just kind of showed you here is not important, but these 2 circular paths, actually, when you worked it out using a formula, it looked like this. When you're plugging these in there, for some reason, Maple wouldn't integrate it this way. It didn't like it. But as soon as I started distributing, like see the minus 5 sine t and the plus 5 sine t makes negative 25 sine t squared. When I multiplied, distributed these out, and combined like terms, it liked it. Actually, we had some terms cancel here. We have a 25 sine cos, and then we have a negative 25 sine cos. So Maple didn't like those 2 integrals right there when I developed them, but then once I combined them, then they turned out being correct, and they turned out correct and yielded 8 pi. So it would not have been a fun exercise, and I don't want to waste your time by going through all the details and of how that was developed. You know, if you're curious, you could ask me, but the Greens theorem would be the way to go on this anyway. So I would never have you evaluate a line integral that complicated, but I just wanted to show you that. Now here's a Greens theorem to evaluate this field here, and this vector field, and here's our path over here. So instead of getting 3 C1, C2, and C3 and adding them together, just don't do that. Let's do Greens theorem. So you see I need nx minus my. So the derivative of this respect to x will be 3y cubed. The my respect to y will be x squared. So the function we integrate is from 3y cubed minus x squared. Now let's look at the region of integration. I'm going to go dy dx here. Obviously you can decide which way you want to go. So now we're back to using our integration skills. So I'm going to integrate that function, and then if I go dy dx, I'm going from lower to upper. The lower is x squared, the upper is 4. So from x squared to 4, and then dx would be just from 0 to 2. Remember, the outer limits of integration must always be numerical. So now it's just a matter of evaluating this antiderivative. So with respect to y, it's going to give you 3/4 y to the 4th minus x squared y. Put in 4, put in x squared, so there's the 4's being plugged in there. Here the x squared's being plugged in there. So just a little messy algebra, but nothing that bad. So then I integrated that. I kind of didn't. In other words, I didn't bother to write out a line showing that that was x to the 8th, nor did I write this as x to the 4th. Now notice though, one thing I'll point out here is this negative and that negative, of course, makes positive. So the antiderivative of x to the 4th would be 1/5 x to the 5th. And actually, once you got this down to one variable, you could integrate it in the calculator if you want to. The numerical integration in the calculator. So there's all the terms. Like I said, just watch out for that little plus right there. So basic antiderivative, put in 2, put in 0, we get 5/056 divided by 15. Alright, now I decided to amuse myself here, and you really don't have to worry about this. So I'm going to kind of, for the sake of the video, just kind of keep this moving a little bit. Like I said, if you ever want to question any of this, you could ask me. But anyway, so I created the 3 paths as if we were doing them as 3 line integrals and adding them up. All right, so I don't want to go through all this. I hate to say that, but but here's the function. So the first one, t squared. So we're substituting t for x, t squared for y. There's dx and dy, or dt and 2t dt right here. I mean, these aren't hard to do, but it's tedious coming up with this paths. You know, once you do that, the math of this is not that hard. These integrals aren't too bad. There's one coming up I'm going to show you that actually is a little rude, but that's why we don't do it that way. Well, this one ends up simplifying to t to the 4th plus 6t to the 8th dt from 0 to 2. The second one ends up being this -4 times 4 minus t squared from 2 to 4. And I just put this in maple. The last one just happened to turn out where this part worked out to be 0 right here. So that's game over there. That's 0. So obviously in the maple I only had to put the first 2 integrals there because the last one's 0. And lo and behold, I must have set them up correctly. Or that would be the luckiest accident I've ever seen. But I got to figure it wouldn't get that number by accident. So there it is. 56 over 15. So the key is that you understood the Greens Theorem part. That's the key, more so than this. So I think I do this at least one other time in the notes here. So, all right, so we have this field, vector field y squared dx plus xy dy. And then the graphs y equals square root of x, bounded by x equals 9, and bounded by y equals 0. So there's the curve with the shaded region. And now let's use the Greens Theorem, which is we're integrating nx minus my. So nx would be the derivative of xy respect to x would be y, minus the my, the derivative of the first term with respect to x. Respect to y, pardon me, would be 2y. So it's 1y minus 2y gives me negative y. So that's the function I'm integrating here, negative y, and I'm choosing dy dx. You could decide if you want to, but since y is a function of x already, I generally go dy dx, just like I did back when we were doing double integrals. So vertically, we're going from 0 to the square root of x, here to here, and then dx, will be horizontally, must be numerical, go from 0 to 9, right there. So now it's just a matter of working out this double integral. So the antiderivative of y will be 1/2 y squared. So then the negative, of course, with it. So I'll pull it out the negative 1/2. Put in square root of x. Gives me x. 0 is 0. So now I just have the integral of negative 1/2 0 to 9 x dx. Pretty darn easy. And gives you negative 81 over 4. Oh, it looks like just for grins, I did write it the other order of integration. I'm not going to go through and work all that out, but I'm sure it's right. You can let me know if it isn't, if you want to check. But that's what it would be, dx dy, because you would change the y equals square root of x becomes x equals y squared. So left to right, you'd be going from y squared to 9, and then 0 to 3 vertically. Alrighty, well, it looks like I did that crazy thing again here, didn't I? Where I broke it in paths. I guess I was just trying to, really show that the answer yields the same both ways. So after this one, I think you'll probably be convinced for sure if you weren't after the first time. Okay, so I created, this time I labeled them C1, C2, C3. Probably should have done that for the first one, but so there are the paths that I created. I think that last integral ends up being something pretty rude. So there's the 3 paths, so we have to add those 3 line integrals together. Okay, and I kind of skipped a lot of steps here. I went straight to the maple. So I just explained that I did the substituting like I did for this problem. I'll just kind of go back up here for a second. So I'm saying, not for this function, obviously, but I'm saying after already doing that without showing the steps here. So, okay, I guess even I didn't want to wear this one out too much either. So actually, I did them separately. I could have done them all one string and added them up. This one looks that integral would have been easy. No, actually, these both would have been easy. Because it wouldn't have been that hard. The radical, I was just worried about that the radical was going to cause some sort of problem. But no, that would not have been that difficult because these would have canceled and then that would have been no radical there. So I was thinking more along like trig substitution or something. But no, never mind. But anyway, we still don't want to do it this way. Because look at the 3 integrals. And then we add them up. And we get negative 81 over 4, which is what we got by Greens Theorem. All right, at least I didn't spend too much effort on that one. I hope I didn't do this one by the other method. No, okay, good. I guess I kind of quit there, hopefully. So we're going around this boundary of this square. Now I just kind of drew the path that it would be taking. Now, of course, we're not going to create that path. I mean, all we need is the area of the square. But the path just shows how you would, if you were setting it up as 4 line integrals, is how you'd have to write them. Because for Greens Theorem to work, it means the area must be on the left as you're going. But it doesn't really matter when you set up the Greens Theorem because you're just going to set up the region for that area right there. So okay, like I said, I used the fancy notation this time instead of just nx and my, but same thing. So the derivative of this one with respect to x will be 2x. The derivative of the first one with respect to y will be x. And so we have 2x minus x. So that's just going to be x. So I'm going to go dy dx. And rectangular coordinates, whenever your region of integration is any kind of rectangle, a square is a subset of rectangles. That's the only time that you'll have a numerical on the inside. Obviously, the outside is always numerical. But I would have said that in one of the earlier on videos in that chapter. But yeah, so it's going to go 0 to 2, 0 to 2. Super duper easy. The answer equals 4. Now, it's just coincidence that it's the area of that square. Because if you have different stuff here, we would have been integrating something different here, and it wouldn't have been 4. Okay, so Greens Theorem's not too bad. This one gets a little messy from an algebraic standpoint, not from a conceptual standpoint, but it's just kind of it's a little messy. But like I say, once you get this down to one variable, you can do it numerically on the calculator. So let's see what we have. So he's got the instructions, Greens Theorem. Already has the answer conveniently marked for us, so that's helpful. And there's the function given. And it's the vertices of a triangle. So let's see. So there's my triangle drawn over there with those vertices. So I have to come up with equation for especially the angled line. I need an equation for. So that's not too difficult. That's just y equals 3 minus x. So we need that obviously to set up our limits of integration. So there's our picture of our shaded region, which would be 3 paths if we were doing them as individual line integrals. So let's figure out, here's nx, so 4xy, the derivative of that with respect to x will be 4y. And then the my, the derivative of the first part with respect to y would be 2. So we were integrating 4y minus 2 from 0 to 3 minus x, and then from 0 to 3. So like I said, once you get it down to dx, you can go to the calculator, it's fine. Well, let's just take a look. I did the whole thing manually, so we're integrating with respect to y, so the antiderivative of 4y would be 2y squared, and then antiderivative of dy, the 2's there with it, excuse me, 2 dy would be 2y with a minus right there. Plug in 3 minus x, plug in 0. So it's going to be 2 times 3 minus x squared minus 2 times 3 minus x. So I FOILed out the 3 minus x squared and came up with this 2. I distributed the negative 2 here, which gives me negative 6 plus 2x. So after distributing the 2 here, I combined all the like terms before I integrated and came up with 12 minus 10x plus 2x squared dx. So now I can integrate that with respect to x from 0 to 3. So this really isn't as bad as I thought it was going to be. So it's 12x minus 5x squared plus 2/3 x cubed. Put in 3, put in 0, and you'll get 9. So okay, that wasn't too bad. Oh, looks like I did this business again. Sorry. Let me scroll down past this. All right, I got, yeah, well, I need to at least kind of make these stand out a little bit. I can't get it. Well, the first one ends up being 9/2. Second one ends up being 9/2. The third one ends up being 0. And 9/2 plus 9/2 plus 0 equals 9. So it did match. So I must have set it up correctly there. But I don't want to go through all this. But I'll just let you look at it here for a second. Of course, you could always pause the video if you were inclined to try to figure that out. But I wouldn't worry about it. Certainly, you know, because I teach this course sometimes in a short summer term or the long fall semester. Certainly, if you're taking the 5-week summer class, I probably wouldn't invest too much time figuring that out. But in a long semester, you might be curious. And I'm just mentioning, well, you know, kind of the obvious here, that Greens Theorem was more efficient. I guess the only way something like this would be better, which is not something I would do to you on an exam, I'm just pointing this out, is if for some reason the line integrals worked out a lot better than maybe the Greens Theorem turned out to be some really, really complicated integral. I haven't run across that, but I guess it's theoretically possible that that could happen, that the Greens integral, but I've never asked one on an exam where it's the Greens Theorem integral is super duper complicated. Yeah, you may have to convert it to polar or something. That might be, that's not too bad, but okay, this one's very similar to the last problem. I mean, in the sense that the graph region is the same. Obviously, we have a different, you know, equation here, and then we have slightly different triangle. Instead of y equals 3 minus x, we have y equals 6 minus x. Yeah, maybe I should have found a curve here or something. That's all right. But we'll go from, here we go. So we have no nx. Nx will be 2x, the derivative of this part, and the derivative of this part, with respect to y, will be 2y. So we have 2x minus 2y. And so the antiderivative with respect to y would be 2xy minus y squared. Put in the 6 minus x, put in the 0. Except this time the squared's at the end and the last one was at the beginning, but it's still very similar. So I FOIL that out. Of course, I realize that this had the minus in front, so the minus is going to change all those terms. This is easy. That's just 12x minus 2x squared. But this minus here makes that negative, positive, negative. Right there, negative, positive, negative. Combine the like terms, easy. And you have this result. Take the antiderivative. And let's see, which is negative x cubed plus 12x squared plus 36. Put in 6, put in 0 at the bottom, and you magically end up with 0, which, you know, may sort of seem a bit insulting, right? You went through all that effort, but I went through all that trouble to get a 0, but that's okay. 0 is a legitimate answer, but this almost seems like it was a waste. So it wasn't like something that was automatically going to be 0 when you looked at the problem. You know, it's not like I could go back and say, oh, well, I knew that was going to be 0. It wasn't something like that. It just happened to work out to be 0. So, or I would show you the shortcut if there was one. Well, that concludes this video on Greens Theorem.